Today we are going to discuss about mineral admixtures. The mineral admixtures which we are going to discuss are silica fume, fly ash, ground granulated blast furnace slag GGBFS, rice husk ash and metakaolin. First we are going to see about fly ash production. This fly ash is obtained in thermal power plants while burning coal, and when we are mining coal, some clay will also be present in the mining action. During the mining action, some clay will also be present in the coal mineral, and when it is being burned, fly ash is obtained. Next, silica fume production. Fly ash, silica fume, GGBFS, rice husk ash, metakaolin. Fly ash, silica fume, ground granulated blast furnace slag, rice husk ash and metakaolin. First we will see about its production, how these mineral admixtures are being produced. Fly ash. When we are burning coal in thermal power plants, we will be obtaining this fly ash as residue. While burning coal, some clay impurities will also be present in the coal, and when it is being burned, we will be obtaining this fly ash as a residue. Next, silica fume. The silica fume is obtained by reducing the high quality quartz with either coke or coal in an electric arc furnace, and when doing so, some gases will be escaping. When we condense those gases, we will be obtaining this silica fume as the product. This ground granulated blast furnace slag is obtained when the iron ore containing clay as impurity is to be removed. That is, when we are processing the iron ore, it may contain some clay as impurity. To remove the clay, we will be adding some lime. That lime and clay will form a molten slag and it will be floating, and when we remove that floating material, we will be obtaining this ground granulated blast furnace slag. This rice husk ash is obtained by burning rice husk. This metakaolin is obtained by firing calcined clay in a controlled manner. In these ways, we can obtain the admixtures. Why these mineral admixtures are called as pozzolan? Why these mineral admixtures, when used in concrete, will enhance certain durability or strength properties? Why it happens so? That is because of the pozzolanic activity present in these mineral admixtures. What do you mean by pozzolans? It is nothing but lime, alumina and silica system. All these mineral admixtures will be having this lime, alumina and silica system within them. These materials are grinded and heated and then cooled rapidly, that is during their production process. When it is being cooled rapidly, the chemical energy gets trapped into them and it results in the formation of amorphous material. That is, they will be less stable in nature. So, it gets reacted quickly in the presence of water or in a conducive environment. So, it is termed as puzzolones. These minerals will be having this lime, alumina and silica system within them, and that is responsible for the binding action, and just they are termed as puzzolones. These puzzolones will contain reactive silica and it will react with lime in the presence of water to form the binding material called CSH gel, which is responsible for binding. We will be discussing about these mineral admixtures under 4 broad categories. First one is physical characterization. Second, chemical characterization. Third, mineralogical characterization, and fourth, mechanical characterization. In physical characterization, it mainly deals about the fineness, specific surface area, particle shape, etc. In chemical characterization, it deals about the oxide composition. In mineralogical characterization, it is whether amorphous or crystalline in nature, but we all know that puzzolones, as discussed already, will be amorphous in nature. In mechanical characterization, it deals about the strength aspects, workability, setting characteristics, etc. Now let's see about the physical characterization of the mineral admixtures. Here I have shown you the mean size, specific surface area, particle shape and specific gravity of fly ash, rice husk ash, ground granulated blast furnace slag, silica fume and metakaolin. The particle shape of fly ash and silica fume are spherical in nature, whereas rice husk ash has a cellular shape and ground granulated blast furnace slag has an angular shape and metakaolin has a platy shape. Then I have shown you about the specific gravity of each particles. The type F and type C fly ash is nothing but a classification pertaining to the fly ash based on its lime content, that is type F and type C. From this we can infer that the specific gravity, the specific surface of silica fume is comparatively high when compared to other mineral admixtures, and rice husk ash also have a higher specific surface area because of its particle shape. Next we will see about the chemical characterization. Here I have shown you about the oxide content composition of different mineral admixtures. What is the content of each oxide composition in different mineral admixtures? How fly ash classification is being done? Type F and type C. This type F contains low calcium oxide, whereas this type C contains high calcium oxide. Based on this content, they are classifying the fly ash into two types. One is type F and another is type C. That is based on the chemical composition. They are classifying the fly ash into two types. Now we will see about the particle shape of each mineral admixtures. First, I will show you type F fly ash particle shape under SEM, scanning electron microscope. When it is being observed under scanning electron microscope, how it will appear, it's being shown. Next is type C fly ash classification, and this silica fume we have discussed already in its physical characterization that silica fume will be spherical in nature. This picture shows the particle shape of silica fume. Next, rice husk ash has a cellular shape. In the second picture, it shows that it has a cellular shape. Next, we are going to discuss about hydration of pozzolana. How this pozzolans gets hydrated. Since it contains lime silica alumina system, it will take place in hydration reaction, but at what point it starts the hydration action we will be discussing now. As we all know that C3S and C2S, when hydrated, it forms CSH gel and calcium hydroxide. These pozzolans, when added to the concrete, will also form the CSH gel and contribute to the strength characteristics. But initially, the silica in the pozzolans will remain as inert material. The silica present in the mineral admixtures, the lime silica alumina system, the silica content will be more. So, I am specifically telling about silica. The silica content initially it will remain as inert in the system. Then from when it comes into action depends upon the availability of lime. This lime availability comes from the hydration reaction of cement. That is, initially when these admixtures being added into the concrete, it won't take part in any hydration reaction. First, the cement gets hydrated and it forms CSH and calcium hydroxide, nothing but lime. And when that lime availability increases, then this silica, this inert silica will take part in action with the lime produced from the cement in the presence of water, and it forms the CSH gel. This is how a pozzolan gets hydrated when being added to the concrete. Now I will show you the hydration picture of a concrete containing pulverized fly ash. This is a early age fly ash and cement, that is the fly ash particles remain as inert material, and first the Portland cement grains are getting hydrated. Then at the later age, after getting availability of lime, this fly ash particles get reacted with them in the presence of water, and in the later matured age, all these fly ash particles are getting reacted and form CSH gel. And this is how the hydration of pozzolan take place in concrete. Next we will be discussing about the pore size distribution, that is when these admixtures are being added to the concrete, how the pores in the concrete are being filled by these mineral admixtures. Since these mineral admixtures will act as an effective fillers, that is when cement is being alone used, it gets hydrated and there will be some percentage of voids, pores present in the system. But when these mineral admixtures are added to the cement, these admixtures will act as an effective fillers, that is the percentage of pores or voids in the system will be reduced due to the presence of these admixtures. Now we will see how these admixtures are acting as an effective pore fillers. Pore size distribution. First we will discuss about the pore size distribution of fly ash. In the graph we have a control concrete, 10% of fly ash, 20% and 30% of fly ash, and the graph is between pore volume and the pore diameter. The graph is between the pore volume, pore penetration volume and pore diameter. At 28 days strength, we are having a control concrete, 10% of fly ash, 20 and 30% of fly ash. And in the graph it shows that the control has less porosity. Control concrete, that is a concrete without any admixture, has a less porosity compared to the concrete which is having mineral admixtures. But what we discussed was, when mineral admixture is added to the concrete, it acts as a pore filler. Then how come this difference is being created? Why the control concrete has a less porosity when compared to the concrete with fly ash? The reason is this fly ash will get activated in the system at the later stage. As we discussed in the hydration of pozzolans, due to the unavailability of lime, it remains as an inert material, and after a sufficient availability of lime, it comes into action, and that's the reason why we are getting a graph like this. Next, we are discussing about the pore size distribution of rice husk ash. Here we are having a control, 10% rice husk ash, 20% and 30%. And here the rice husk ash shows, that is the rice husk ash with 30% replacement shows less porosity when compared to the control concrete. The reason behind this is, this rice husk ash having a higher specific surface area gets activated quickly, and just it fill the voids in the system, and that's the reason here we are getting a graph like this. There in fly ash, because of its later action, the control has the less porosity when compared to the fly ash replacement, but here in rice husk ash, because of its high specific surface area, it gets reacted quickly and fill the pores, and so the 30% replaced rice husk ash has a less porosity when compared to the control concrete. Next, pore size distribution of slag. Here we are having 70% slag and 30% slag. Here the porosity of 30% slag is less when compared to that of the 70% slag. The reason is again the hydration of pozzolan, how it's being hydrated. Since the slag percentage is high, here the 30% slag has a less porosity when compared to that of the 70% of slag. Next, pore size distribution of silica fume. Here again, without silica fume and with silica fume, we are seeing the difference, that with silica fume, the pore intrusion, that is the pore volume, is filled. With silica fume, the porosity is reduced when compared to without silica fume. Next, about the setting characteristics. When this mineral admixture is being added to the concrete, it does not adversely affect the setting time of the concrete. The setting time characteristics is being obtained by doing consistency test. That is, a particular cement should have a initial setting time like this and a final setting time of not more than 10 hours. And when these admixtures are being added to the concrete, it does not adversely affect the setting characteristics of the concrete, so that it can be used in the system. Heat of hydration. Next, we are discussing about heat of hydration. When these admixtures are being added to the concrete, how it behaves, how the heat of hydration of the system gets altered or it remains the same, we will be discussing. When we discussed earlier about heat of hydration, the main component which is responsible for heat of hydration is C3A, tricalcium aluminate, that reacts with gypsum and forms the ettringite. This is the first hydration process, and from this the other process continues, and that C3A is responsible for the higher heat of hydration, that is high amount of heat will be liberated from the hydration of C3A. Here, when mineral admixture is being added to the concrete, heat of hydration of a system is lowered. When cement alone is present, then the C3A first gets reacted, and after that the other compounds get reacted and the hydration reaction proceeds. Whereas when mineral admixture is added to the system, that is, we are replacing some amount of cement by this mineral admixture, so that part of the cement alone gets reacted, and from that, based on the availability of lime, this pozzolans get reacted. So obviously we are getting a less heat of hydration when compared to the normal concrete system. So while by adding pozzolans to the concrete, we are getting less heat of hydration. Again, this heat of hydration of all pozzolans will not be, this heat of hydration will depend upon the particle size of the admixtures used. Fly ash and GGBFS will reduce the heat of hydration, whereas silica fume will increase the heat of hydration. This difference is because of the particle size effect. Since the silica fume particle size is comparatively less, it influences the heat of hydration in the system, whereas fly ash and GGBS will reduce the heat of hydration. This silica fume will increase the heat of hydration. This is due to the effect of particle size of silica fume. Now we will see a graph For this heat of hydration, the y-axis shows the temperature plot and the x-axis shows the time after placing, that is in days, and the control concrete after 4 days, that is between 4 and 8 days, the control concrete shows a higher temperature when compared to that of the fly ash concrete, and this is how the fly ash, when being added to the system, reduces the heat of hydration. And another example, a raft beam of thickness 5 meter, in that the temperature increases in the x-axis, that is 40 degree, 60 degree and 80 degree. Here the control concrete has a maximum temperature at the middle of the raft, and the next highest is the fly ash, that is comparatively it is less than the control concrete, and slag concrete has a temperature even less than the fly ash concrete, and this is how the heat of hydration is reduced in the system when we are adding admixtures to the concrete. When fly ash is being added into the system, into the concrete, it does not demand for higher water content, that is less water content itself it can ensure cohesiveness and also better workability because of the particles being spherical in nature. Water demand of silica fume. Silica fume also has the same spherical particle size as that of fly ash, but when this silica fume is being added into the system, it demands for a high, it requires a high water demand. The reason is the particle size being spherical, but the specific surface area being relatively high than that of the fly ash. So, even though it is spherical in nature, when the silica fume is being added into the system, it requires high water demand. That is, the fineness plays a role. There the fineness is, in fly ash the fineness is comparatively less, so it does not require high water demand, but here the fineness is so small, but here the fineness is less and it requires a high water demand. Whereas this GGBFS does not increase the water demand, but when rice husk ash is being added, because of its cellular in nature, it increases the water demand in the concrete. So, we have to ensure that what type of mineral admixture is being added to the system, so that the superplasticizer demand will not be affected. When silica fume is added to the system, there we have to ensure that sufficient superplasticizer is being added to the system to ensure the proper workability. If it not, then it gives rise to the cohesiveness workability issues because of the silica fume particles having less fineness compared to other mineral admixtures. The silica fume and the silica fume increases the water demand because of its fineness, the particles being so fine in nature, whereas rice husk ash increases the water demand because of its cellular in nature, whereas the fly ash and GGBFS will not affect the water demand to that extent. Next, we will discuss about the strength characteristics. When here we will see a graph plotted between strength and age, and First, the blue color line represents the OPC, ordinary Portland cement, and the red color line represents the OPC plus fly ash, that is the fly ash being added to the system. At 28 days, at the early stage, before 28 days, the OPC curve remains in the peak when compared to that of the OPC and fly ash, and after 28 days, the strength of OPC and fly ash has increased when compared to that of the ordinary Portland cement. And that is, when fly ash is being added to the system, the early strength remains less compared to that of ordinary Portland cement, but at the later strength, it achieves the strength greater than that of the OPC. This is the scenario when fly ash is being added to the system. Likewise, the ground granulated blast furnace slag also will behave in the same manner as that of the fly ash, that is, the early strength development will be less when compared to that of the later strength development. Whereas, when rice husk ash and silica fume is being added to the system, they are highly reactive pozzolenes and will initiate the hydration reaction in the beginning itself, and it paves way for the early strength development. Fly ash and GGBS will enhance the later strength development, whereas rice husk ash and silica fume will initiate the early strength development since they are highly reactive pozzolenes. And with this, we have discussed about the physical characterization, chemical characterization, mineralogical characterization and mechanical characterization related to strength, setting and workability characteristics. When admixture is being added to the system, how it alters, these things are being discussed in detail.